So this Monday, we just stop here. Then we start to understand what the rational derivative is. And later on, I also show you what is the gradient vector. So let me just spend some minutes to review about the idea for the directional derivative. So the derivative of f of sy at this point, s0, y0, in this spatial direction, then normally they may give you a direction only, but you need to, you just make it, you just need to unitarize it. I mean, you should just normalize it as a unit vector. And later I will show you example, but before that, I will show you the concept first. So it's the number. So just notice it's a number. So as I told you last time, that why is the number? Because finally it will be the slope for this tangent line. So the typical the presentation for the directional derivative is just like this one, df over ds. Okay, so you can just notice that it is about trying to evaluate a small change in s, how much will be caused in the f's value. So df here is the change of the f value, right? And then you can notice that there are two very important parameters. One is u is here. Then p0 is this point. Now we just define it as this one. Okay, and next time I already give you a rough idea about the directional derivative. So this time I will give you more explanations for each part. So okay, let me just emphasize the idea again that if we want to calculate df over ds when the direction is u and the point is p0, what are we talking about? So you can just image that this is s, this is y, this is z, right? So when I give you f, so f here can be defined of s, y, and the return value is z. This is the first very important parameter. So once I give you this f, then you can just get this series, right? According to f here, you can get the series. Then I also give you a very important, another important parameter p0. So p0, suppose p0 is here, s0, y0, right? Here's the second one. And then the third one is u, right? U means following some direction, and it is a unit vector. Okay, so compared to that, I try to also focus on the sy plane. This is s, this is y, right? So when I give you z is equal to f of sy, then maybe the surface is just here, right? This is z is equal to f of sy, but z is here, right? Z is here. S1, z is here. But if you just follow the Furby on the top of the surface, you can just, and then just look downward, you can see the surface is here. So I just focus on sy, so I just try to match sy plane to the right hand side, especially just in the sy plane. So if P is here, P0 is here, and this is S0, Y0, right? And then we have U direction. So following this, then we can get the cutting plane, just like this one, right? I just use this cutting plane to have the intersection with this. So that means the cutting plane will be just like this, pass through the surface, right? Just like here, just like the left hand side, we can get something like, maybe I just use different color, something like maybe something like this. Through this cutting plane, you can have an intersection like this curve in orange, right? And especially the point will be mapped to some important point. This point will be S0, Y0, then F of S0, Y0. This is a 3-dimensional point, right? By using P0, S0, Y0 to be mapped through this function, so you can get the height is S0 of S0, Y0. Okay. So we try. I just give you the concept about this first. Then we just define as the previous slash. By this size show, we just define as this one. I just repeat it again here. So okay, it will be df over ds u t0 as limit s is a 0.0, then f of s0 plus s0 plus then u1 u2, later I'll explain to you, so no worry. Then minus f of s0 comma y0 over s. So what does it mean? It means, okay, following this, P0 is S0, Y0. Following this direction. So all points. So you can just regard U as U1, U2. Or sometimes we note it as U1I plus U2J, right? Right, I focus here. So by following this is the starting point and the direction is U. So all points in a line, all points in a line, you can express it as Sy is equal to the start point is S0, Y0 plus U1, U2, then S. So did you notice that actually this is a parametric equation, right? This is for x part, this is for y part, but through this parametric equations, we can just represent all points as y, any point as y here, by using S0, Y0, and also U. Right? This is U, and this is P0. So all points here can be represented as this one. So So that, for example, if I use another point, if we just follow this way, then we can get this point is S0 plus U1S. This is U2, U0, Y0 plus U2S. So it's a kind of that. This is P0. Okay, this is P0, S0. So apart from this original point, we can find another point here. So this point is just this point, right? And this point is just like this point. Then this point will be S0 plus U1S, comma, Y0 plus U2S, right? By using the parametric equations. So this point can also be mapped. To another point. This is a 3D point, and this point will be S0 plus U1S, comma, Y0 plus U2S. Then f of S0 plus U1S, comma, Y0 plus U2S. Right? So you can see S0, Y0 will be mapped to this 3D point. And another point is this one, that we can map another 3D point, right? So if you use this pi minus this pi, so did you notice that? This high is this one, right? And this high is this one. So we are trying to get its difference. So the difference for f over the difference for s, and we just take this limit s is approaching 0. You can just notice that actually it's just talking about the tangent line, right? So as this point is getting closer to this point, that means when s is 0.0, you can see this green point, this origin point is getting close to the yellow point. Then finally, once the origin point touch the yellow point, then you can get the tangent line. You can get the tangent line. And the value will be the slope for this tangent line. OK， 了解吗？我解释一下哈。它定义成这个事实上是很有意思的哈，就是说，它想表达就是任一个方向的导数，任一个方向的导数，我们之前讲过的x 偏微或 y 偏微，其实它都是很特定的某一个方向，一个是 x 是常数的，一个是 y 是常数的切法。可是现在我们想要把它更怎么讲，更一般化，把一般化嘛 generalize。那怎么做呢？起点很重要，对不对？我们当时在算单变就是那个偏微分的时候，其实也要考量这个 S0、Y0 在哪里，对不对？但是那时候我们没有特别的指出 U， 因为那个 U 是很特别的。等一下我们来考虑一下那个 U 会是什么哈。好，我们现在 U 是任意的，那请大家就对照右边这边，我把那个 SY 平面特别把它拉出来。好，左边这个是一个三维的图形，右边是 focus 在 SY 平面上。好，原来这点 P0 S0 Y0 呢，如果对应到那个 Z 等于 F(S1)， 你说这个曲面上的高度它会得到最高进来，对不对 ？S0 Y0 F 的 S0 Y0， 对不对？ 同样的，如果我把这个 P0往这个 U 方向走，这个 U 方向当然可以往这边走，可能也往负的走。记不记得参数式？我这个 U 虽然是往这边走，可是这条线是有包含正的 S 跟负的 S 的。那我们假如这个是正的 S 好了，它离开它一点点的时候，我们利用这个参数式来表达，就可以表达成 SY 从 S0、Y0 当起点 ，U1、U2 当方向的 S 单位，它的长度，它就走了这么长的地方，因为它是单位向量，所以它走的长度这么长的情况之下，它的点就会移到了这个S0 加 U1S 跟 Y0 加 U2S 的地方。好，我们再把这点对回来这边看，它就是远离它一点点的地方，这个点是这个点，对不对？但是它的高度有多高？应该把它带到这函数的上面去嘛，所以我们就得到这个三维的坐标点呢，应该是这个 S0 加 U1S 逗点 Y0 加 U2S 逗点把这个 S1 带到 S 的高度，所以我们就会得到这两个点是它的高度落差的，对不对？把它的高度落差呢去除以 S， 是不是就好像是在算它这边的切线？这个把是算的是应该是两点之间的连线嘛，连线的斜率除以 S。但是当我们把 S 推到趋近零的时候，这个瞬间呢，这个橘色点碰到这个黄色的点，就引发出我们算出来这条红色的切线的斜率。所以这个当然这个 U 也有可能是从这边过来，还记不记得我们当时在讲导数的时候讲过那个概念？我可以从左边过来，我也可以从右边过去，对不对？但前提是这两个不管，当我们写 S 趋近零的时候，复习一下上学期讲的 S 趋近零它有两层意义，一个是 S 趋近零 plus 跟 S 趋近零 minus， 所以它有可能是从这边过来，只是我这么举的例子可能是看起来比较像是正的那种方向，对不对？但是你要保证这两边的极限要存在。如果是极限存在，这个极限我就称这个的方向导数。对，来，那我们来问大家好了，当初我们讲的对 x 的偏微分，对 x 的偏微分也是这个例子里面的其中一个 special case。那对 x 的偏微分来说，它的 u 是长什么样子？那 u 应该会长什么样子？知道我在讲什么？如果我们今天考虑这个 partial f partial x， 对不对？那它对等的应该会有它的 u 咯，对不对？或者是我们考虑的 partial f partial y， 它也是一个方向导数，只是很特殊。它这个 u 应该会长什么样子？记不记得我刚才讲说，如果对 x 偏微，谁是常数 ？y 是常数，只有谁在变？只有 x 在变，对不对？所以如果只有 x 在变，它这个 u 应该是什么？10还是01？10，对不对？是不是10？所以它在这个例子下，它的应该是10。相反的，在这边的时候呢，它刚好是01，对不对？因为我们在对 y 偏微的时候，对 y 偏微是 y 在改变，但是 x 是不变。x 不变，那个方向呢，应该是 s 方向是没有改变的，只有在这个 y 方向有在改变。所以这是它的很特殊的两个偏微分，这两个偏微分是很两个特殊的方向导数。那还记不记得上个礼拜，这礼拜一我讲过，两个有方向导数的不一定可微分，为什么？因为你只考虑了两个方向。从这个角度来看，你就可以看出这个 u 其实是可以四面八方的，对不对？是不是可以四面八方的？这个 u 事实上是可以四面八方的，对不对？所以除非你可以确定每个四面八方的这个方向导数都存在，那它就可微分了。可微分了，它就延续。但是你如果只探讨说我两个偏微分存在，其实不够。 你只讲了两个切面，那个切法有切出来，有导数。好 ，OK。So the concept is very important. Special. This is a two special case. This is two special cases. Okay. So then we start to see how to calculate this one. So if we want to calculate df over ds, then the direction is u, then the point is p0. How can we do? So we can just follow section 4. F original is determined by xy, right? Original is determined by xy. Then, so we have a h to x, then another h to y, right? Then these two factors are determined by s and y, determined by s, right? Because s0, y0, and also u1, u2 are constant, right? So then we will determine by s. So by the chain rule, we can get here should be partial f, partial x. Here is partial f, partial y. Then here is dx over ds, dy over ds. So we can get partial f, partial x times dx over ds plus partial f, partial y times dy over ds. And the special here is for P0, right? For the special point P0. Okay. So we have another one times then plus together so that we can get this expression. And then we can continue to simplify that. That will be partial f, partial x, p0 times u1 plus partial f, partial y, p0 times u2. Why can't we just get this one and this one? Because did you notice that s is equal to s0 plus u1s, right? And y is equal to y0 plus u2s. So when we just differentiate x with respect to s, then this is constant. This u1 is also constant, but s is a variable. So the answer will be u1, right? So you can regard this as differentiate respect to s for s0 plus u1s. So you can get this one. And this one is ds over y0 plus u2s. So you can get u1 and u2. Okay? Then we also can have another expression. Partial f, partial x at p0, I plus partial f, partial y at p0, j. So this expression is in a vector form, right? I and j. If you remember, I is the unit vector for x direction. J is the unit vector for y direction, right? Then this vector, this vector dot u1i plus u2j. So you can see this is the u vector. Then here we just define this as a very special vector. We call it gradient f at p0. Then dot together. Okay, so first we just use chain rule, which we just learned in session 4, so that we can have this expression by the tree diagram, right? Then we can just continue to get this one, right? Actually, this is u1, this is u2, because you can find these two parameters, parametric equations over there, here, right? Then we can get u1 and u2. So this term times this term plus this term times this term. So we can just move. We just use the vector form to express it. Then you can get this is this spatial vector dot u1i plus u2j. Actually, this is the u vector, right? So we can have a u here. And this is another spatial vector here. We call it gradient vector. So the gradient vector, here we define it as P0 is the gradient of f of sy at P0, S0, Y0. So you can notice that if we want to calculate gradient vector, there are two important parameters. The first one is f of sy. The other one is P0. Then the formal definition is equal to partial f partial x P0 I plus partial f partial y P0 j. So this is very important. This is very important. This is a so-called gradient vector. So if we can get a gradient vector here, we just simply get u, then we just using dot operation on these two vectors, and then we can get the directional derivative. Okay, so I just immediately give you an example so that you can just know how to apply this. Please just find the derivative of f of xy is equal to s times e to the power of y plus cosine sy at 2, 0, this point. And in the direction of V is equal to 3I minus 4J. So this is the complete description for the question. So find the derivative. Okay? Find the derivative. But the derivative you need to follow this direction. This direction. Then I also give you the surface provided by this equation. And I also give you the point. Right? So here is P0. This is something about U, right? But actually this is not U. Why this is not U? Because when we just use the expression, it should be univector, right? But right now, V is equal to 3I minus 4J is still not a univector. So we need to normalize it. Then this is the surface, right? So you can see three key factors when you just want to get the direction of the derivative, right? So the first thing for us is, right now we already identified these three key factors. So the first one is we need to try to convert it into a univector. So if we want to get the U, it will be this V over V's length. So that it will be 3I minus 4J times over its length, 3 squared plus minus 4 squared. So the answer will be 3 over 5I minus 4 over 5J. So right now it's univector already, right? So this is the univector for this direction. So when I give you the direction by this vector, actually it is still not a univector. So we need to try to normalize it to get the univector. So right now, U we already have, right? Because we need to meet, we need to fit this formula. So we already have U, right? So the next step is we need to try to calculate its gradient. So gradient is partial f partial x at P0, partial f partial y at P0. So we need to calculate partial f partial x at P0. Then also have partial f partial y at P0 also. So this is about the calculation for partial derivative. So it will be based on this. This will be e y to the power 1 minus y times sine xy at P0 is 2, 0, right? Similarly, for the partial f partial y, it will be s times e to the power y minus s times sine xy, then also at 2, 0. So that you can just use s is equal to 2, y is equal to 0 as the input for this part. So through some calculation, I will skip the calculation, then the answer will be 1, and this one is 2. So through this, we can get the gradient vector f at 2, 0 is 1 I plus 2J, right? 1 comes from this part, 2 comes from second part. Okay, so right now we already have U. We also have gradient vector. So right now we just try to use the dot operation on these two factors so that gradient. So the df over ds at p0 follow u direction, and then the p0 is equal to gradient f to 0 dot product to u. Then it will be 3/5 times 1 and 2, then adding together, and then the result is -1. So -1 means is decay, right? Did you remember? But we just calculate the slope. If the slope is positive, that is talking about is just increasing, right? But if it's negative, it will decreasing. At that point, following the cutting curve, cutting plane, then we can get a curve. Then at that moment, it will be decrease. The value will decrease. So you get -1. So, but maybe I forgot to tell you that sometimes the notation also can be. That is not that important, but sometimes the expression can be represented as du then f over p0. It's also fine. This is just another expression. So either this one or this one is fine. But just remember, it should be follow this step. 这很重要哈。这个题目就很快验证一下这个怎么做哈。我把它缩小一点，跟大家再说明一次啊。所以，如果我们要算方向导数呢，这个题目非常重要。这个题目呢，也会在期末考的时候一定会考的，不是这个题目了哈，不是这个题目，这个样态的题目哈，一定会考的。那这个其实我们不用担心，你只要 follow 这个公式呢，一步一步就会找到这个算出这个结果了哈。所以你看，他说要找出一个函数，两个变数函数。它的方向导数呢，在某一个点上面 follow 这个方向，所以我请大家记得，你只要这个题目一出来的时候，先确立的3个变数你都有拿到。我为什么一直强调这个？因为等一下我们用到这个观念，所以我们现在要大家先记起来，就是这3件要算方向导数的时候，有很重要的3个因子一定要先抓出来。等一下我们会反个方向来看这个方向导数的问题，但是先正面的去了解到这方向导数的时候，你必须要掌握出3个很重要的因子。第一个，曲面起始点跟它的方向哦，所以刚刚再回忆一下，曲面白色的，起始点黄色的这个点往哪个方向啊？那切出来的这个方向导数呢，就会是什么呢？会是它的 gradient vector 去跟你的 gradient vector 跟你的那个方向的方向单位向量呢去做内积，所以当它到这3个参数先确立出来之后呢，曲面有了，起始点有了，方向有了，有一个小小的陷阱在这里，就是这个方向给你的只是方向。它并没有告诉你它是 单位向量，所以这边常常有时候同学会忘掉了，就直接拿它来做内积，这是错了，因为它必须要单位向量，所以我们这边呢还没开始做之前，要先对它做一个单位向量的运算。所以本来是3i 减 4j， 事实上单位向量的话，它正确的单位向量应该是3/5i 减掉4/4j， 所以差了一个1/5倍的条件，因为它没有除以长度，所以这个才是我们要的 u 哦，千万不要拿这个 v 就去拿去做内积。接下来呢 ，gradient vector 的部分呢，就是一个是单位上面的，一个是 x 偏微，一个是 y 偏微，那在特别是这2个点上面啊，大家去计算，这都是计算的问题啊。但大家有没有注意到，事实上它是勾勒一个什么东西哈？我们在讲这个方向导数的时候，虽然讲的是各个方向，对不对？可是基本上呢，它其实可以由这方向导数啊，最后可以由 x 的偏微分跟 y 偏微分当2个基底。哦，这个如果还没有学过线性代数，没关系，我先讲什么是基底。其实你已经学过了。我们在 xy 平面上面有2个基底，一个叫做10，一个叫01的。你有没有想过，平面上面的所有的 xy 点都是由这2个基底所组成的，对不对？如果有一个平面上有个点叫53的，它是由谁组成？5倍的10，再加上3倍的01组成的。你在平面上任何一个点，最重要2个基底就是01跟10跟01，分别一个是代表 x 方向，一个是代表 y 方向。那所有的其他的任何一个点，其实都是由它们2个线性组合出来的。所以同样在方向导数里，你会发现它也有类似这种关系。x 方向的偏微分跟 y 方向偏微分，事实上就是它的基底，由这2个基底去建构出来其他的方向导数，那差别就是这个 u， 对不对？哦，所以我们再把这2个向量呢做内积之后呢，就会得到这个-1。那-1呢，刚刚有解释过了，负的代表什么？下降的，正的代表递增的。所以再回过来想这张图，所以你可以想象的，在这个点沿着这个方向导数的时候，在那个瞬间它是往下掉的，那个曲面是往下掉的。如果是正的，那个曲面沿着那个曲面走的瞬间，它是往上爬的，这很重要哈。等一下，为什么我会重复讲这些观念？是等一下我们在讲的是我们在控制其他变异的时候，哪个方向可以递增最大，哪个方向可以递增最多，递减最多，哦，会变成用这几个因子当做我们考量的一个基础哦。Okay, so let's just continue. So if we want to calculate d in some direction u for this surface f, it will be equal to gradient f dot u, right? By this, right? But right now I didn't point out any p0, but following this, then we know we can just express the directional derivative as this one. So based on this is dot product, right? Or inner product. So it will be the length of this vector times u times cosine theta, right? Did you remember I told you that if u is equal to u1 plus u1i plus u2j, then v is equal to v1i plus u2j. When we talk about u inner product v, that will be u's length times v's length times cosine theta, right? Or u1 v1 plus u2 v2. When we talk about inner product, right? So where theta here is the angle between u and gradient f. Because gradient is a vector, u is a vector. So when we just calculate its inner product or its dot product, it is equal to its length times u's length times cosine theta. Theta here is the angle between u and gradient f. Okay, so there are three conditions. So we can conclude that here gradient vector f length, u's length. So can you tell me what is the length? What is 1, right? So that we can just even simplify as this length times cosine theta, right? Cosine theta means if this is gradient f, this is u, then this is the angle between. Right? So finally, we can just notice here. So we can just have three discussions. The first discussion is the function f of xy will increase most rapidly while cosine theta is 1. So we all agree with that. Cosine, the value for cosine function is the maximum value is 1, right? The minimum value is negative 1. So if we want to increase most, that means we try to maximize this number. We try to get the maximum number for this part, for this directional derivative, right? So but this is positive, always positive. We cannot change it. But cosine theta can be varied from positive 1 to negative 1. So when cosine theta is 1, can cause this number to be a maximum number, right? So that's why we say the function f of xy can increase most rapidly, quite rapidly. If we say rapidly, that means it's about the change in speed, right? So if we can increase most rapidly, there must be when cosine theta is 1. So if cosine theta is 1, so that means theta is 0. So we can conclude that the derivative in the direction is duf is the gradient vector's length, right? There is a hidden 1 here. Actually, it times 1, so we can just hide this 1. So this is in this direction we can increase most rapidly. The second one, the function f of xy will decreases most rapidly where cosine theta is -1. So that means the direction is totally opposite. So the theta should be pi, right? So we can say the derivative in this direction is dUf is equal to still the gradient vector's length times negative. And also for this direction is the direction is the opposite of gradient f. So that means negative, right? Because it's theta is pi, so it will be the gradient vector's opposite direction. The third one is, let me just summarize the conclusion first, and then after the break, I will show you an example. Any direction U, which is orthogonal to the gradient vector, is a direction of zero change. Why I say that? Orthogonal to gradient f, that means the theta here is 1/2 pi, right? Because if U and gradient vector is orthogonal, the angle between U and gradient f is 1/2 pi. Since theta is equal to 1/2 pi, so that the directional derivative is equal to the length of the gradient times cosine 1/2 pi, so that the answer will be 0. Did you remember when we say the slope is 0? The slope is, if the slope is 0, no change. So we say 0 change. So we can classify into these three types. Okay, so after some break, we come back to the class and I will show you an example. For example, please just find directions of maximum, minimum, and zero change for f of s1 is equal to s squared over 2 plus y squared over 2 at 1, 1. So compared to the previous example, you can notice that, okay, by this, I can get the service, right? Did you remember 3 factors? The first one is the equation to represent the service, right? F here is already here, right? The second key point is which start point, right? This is F. So right now, the question is just asking you about the direction. So in the past, I will give you three factors: F, P0, and U, right? But right now, the question is asking you based on the given F service, based on the start point P0, but you need to answer me which direction can cause the function with a maximal change, with a minimal change, or zero change. So the direction will be the answer you are looking for. Okay. And then based on this example, if you can try to draw this curve. So this curve, you can also use the level curve to draw this curve. So basically, the curve, just like this one, is just like a ball. Ball. It's like a ball, right? Then this is, and this is f of sy is equal to s squared over 2 plus y squared over 2. Then I give you the P0. P0 is here. This is 1, 1, right? So you can just image that if, so right now we are trying to find the directions. So the first thing we need to get is gradient vector. Did you remember if the angle between u and gradient vector is 0, then we can make the function increase most rapidly. So that's why we need to calculate the gradient vector first. The gradient vector 1, 1 here is s when point is 1, 1, I plus y at 1, 1, j. So we can get, after some calculation, it will be 1i plus 1j. Right? So this is the gradient vector. So we can get the gradient vector is in this direction. This is 1, 1. Just remember, this 1, 1 is different from this one. This is about the point. This is about the direction. So we can get the gradient vector is like this direction. So according to the discussions here, we can see if the direction just follow the same, just follow gradient vector, we can have f of sy increase most rapidly. So if the first case, if u here is equal to 1i plus 1j over 1 square over 1 square, and then taking the square root of its sum, then the result is this one. We can have f sy increase most rapidly. So that means if the direction is here, but the length, this should be 1 over square root of 2, 1 over square root of 2. So the u should be follow the same as the gradient vector 1, 1. But the length should be this one, because the length should be 1, right? So the vector will become this one, because we need to try to get its unit vector by 1, 1, right? So if follow this u, we can see u will increase more. So did you notice? You can just imagine this as a ball, right? 这像一个碗一样，对不对？等一下吃饭的时候，把学校如果那碗先拿起来端详一下，再开始吃，好不好？你想一想哈，if the point 1, 1, we can just map. We can just map the 1, 1 here to here, right? The point should be 1, 1, then 1, right? So if you just follow this direction, 1 square root of 2, 1 over square root of 2, you can just see the direction will just follow this way. Right? So it will be, this case, f will increase most rapidly, right? Just imagine that along this curve, this will just increase most. Then, what direction will just decrease most? If we just along negative gradient vector, so that it will be equivalent to u is equal to negative 1 over square root of 2 I plus negative 1 over square root of 2 j. So this time, if you just follow this way, then we can get f of sy just decreases most rapidly. Okay, so what direction? This direction will be, maybe I can use this one. This direction will be this one, red one, right? So this direction will be negative 1 over square root of 2, negative 1 over square root of 2. And then you can just notice that if we just follow the surface, then that will be this way. Maybe I can use different color. Oh, let's see. Okay, still use red. Okay. So this direction is in the xy plane, but if you just follow this direction, you can just find the point will just falling down by following this curve. And follow this curve, you can see it will decreases most rapidly. The third case is along some n, which is negative square root of negative 1 over square root of 2 I plus positive 1 over square root of 2j, or this one if we just follow this one, okay, maybe let me. Oh, wow. Something wrong. Okay, maybe let me just increases most. Then if along negative gradient is equal to, when u is equal to 1 over square root of, this is the second one, then f of s1 decreases. Then the third one is along n is equal to, it's a bit loss. Then we can get f of s1 just is zero change. So, here the first one is should be here. Then this vector will be this one. The second one will be this one. Negative square root 1 over square root of 2i plus negative 1 over square root of 2j. Then the third one will be this one. So either this way or this way. And you can just have a comparison that one is for this direction, one is for this direction, and the other one is for this direction. Right? So for this direction, we can just follow this series, and then we can have f of s just increase most rapidly this way. If follow this way, we can just decrease most rapidly. You follow this direction, which is orthogonal to the gradient vector, either this one or this one. You can just see the corresponding point. We just follow this path or this path, and that will be zero change, right? Because the height is kept the same, right? So that will be zero change. 所以大家想一想，这个碗的例子是最好的。你爬山的时候，你可以想一想，哪一边的gradient，如果你知道那个曲面长什么样子，你如果知道那个山的surface， 你就可以算出它的gradient vector。如果你算出那 gradient vector， 你就知道往gradient vector 那个方向走是爬得最累的，对不对？对不对？所以这个才说我们要去爬山啦，对不对？只是很可惜，我们不知道那山的函数是什么，对不对？但是如果你知道山的函数，你就可以想象，我就在往那 gradient vector 的方向走，那个方向呢，一定会爬得最辛苦。但是如果往 gradient vector 的反方向，刚好是下山的最辛苦，就下降速度最快。但如果跟 gradient vector 刚好是垂直正交，就刚好就是平缓的，刚好在同一个高度上走。 Okay, then I will deliver another concept for gradient. Because gradient, we can apply gradient vectors to different applications. So I will introduce the first one, gradients and tangents to level curve. So if f of y has a constant value c along this position vector. Did you still remember position vector? It's also fine. I can just remind you that you can just regard this is a path. This is a path. But the point on the path is this is x, this is y. So that means f of g of t and h of t is always c. So you can see if f of x has a constant value c along this path. So this path, there are many points in this path. So if we just use this position vector to describe the path, so that means s will be g of t, y will be h of t. So all of s y pair, which is g t comma h t, to represent the point on this curve, then their function value is always c. So we can regard this as a level curve, right? So we can say actually this is a level curve for f of sy is equal to c. I remember, if you still remember, if you forgot, please just go back to review the concept about level curve for f of sy is equal to c. So that we can have this one, right? So we can have this one because all point could be the input for this function, and the function will return the comma c. So we can describe as this is s, this is y. Then this curve, we can say this is r of t is equal to g of ti plus h of tj. So all points in the green curve, its corresponding function value will be c. C here. So we can say this is a level curve for f of sy is equal to c. Then we already have this one, right? So we try to differentiate f of g of t comma h of t is equal to differentiate c. We just differentiate at both sides, right? So for the left-hand side, we can have partial f partial x dg of t over dt plus partial f partial y dht dt. So this is through chapter 3 section 4 chain rule. For the right hand side, it will be 0, right? So based on this, we can just put them together to partial f partial x I plus partial f partial y j. Dot product g dt over t dt, comma g dh of t dt I plus j is equal to 0. So if two vector, these two vector is their inner product is 0. That means these two vectors just are orthogonal to each other, right? And especially this part is gradient vector. This part is velocity vector. So we can conclude that gradient vector, if in this case, following this level curve, when you calculate its gradient, and this gradient will be orthogonal to its velocity vector. What is velocity vector? So if this is a position vector, then for example, if for this point, this might be its velocity vector, and this will be its gradient vector. If here we can get its gradient vector, its velocity vector will follow this way. If this is the point we just focus, we can get its gradient vector, then its velocity vector will be here or here. Because based on this fact, gradient vector is always orthogonal to its velocity vector. So here, this is the position. Its velocity should be just follow its tangent, right? And this is its gradient vector. So if we can get this point, if we know this point, we also know this one, then we can get this. We can have the fact that gradient vector must be orthogonal to velocity vector. So I can give you a simple example. But if this example is, I just explain this explain this example too fast. Next week I can just review it again. So, for example, please just find an equation for the tangent to x squared over 4 plus y squared is equal to 2 at the point -2 and 1. So what is this? That is talking about it. We can see this is a ellipse, 椭圆. Oh. Which is this one, right? Then find an equation for the tangent to this ellipse at the point -2, 1. -1 is here. This is -2, 1, right? This question just asks you to find the tangent. Please find the tangent. Okay, so you can just use the skill you learned from last semester to get this one, but using implicit differentiation, right? 这个题目你可以用上学期所学的隐函数微分，对不对？有讲过嘛？哈，有讲过。But you can also use the skill we learned here. So the ellipse is x squared over 4 plus y squared over is equal to 2. You should regard this is a level curve of f of sy, which is defined as x squared over 4 plus y squared with c is equal to 2. 这个抛物这个椭圆线，我可以把它看为是什么？看为是，如果我定义一个函数叫 f(s1) 等于 x 平方加4加上 y 平方 ，this is the surface, right? I can regard this as its level curve when c is equal to 2. That means all point here, when we use the point as the input for this z is equal to f(s1), it always returns 2 back to represent its height, right? So this time we just regard this ellipse as the level curve for this one. So based on this definition, we can get its gradient f at -2, 1. So we can get s over 2 when point is -2, 1. I plus 2y when point is -2, 1, j. So it can get -1 plus I plus 2j. So this is the gradient vector, right? So the gradient vector is here. The gradient vector is -1, 2. Right? So I give you this point and regard this as the level curve, and I also get this gradient vector, -1, 2. So according to the previous slideshow, the velocity vector, so velocity will just follow the tangent, right? 速度应该会跟这个瞬间是正切的，对不对？ So based on this, gradient vector must be orthogonal to the its velocity vector. So right now we already know this vector. So if we want to express the yellow line, any point here, sy on in this line, in this direction, we will have any point in the line when we calculate its vector minus 2 minus 1, then inner product to its gradient vector, it should be 0. So finally, you can just get it will be s minus 2y is equal to -4. So that will be represent this line. Okay, so this is for this session. No worry, next time I will explain this idea to you. But at least today you must remember you just learned about the gradient vector and how can we just use gradient vector to calculate which direction you can get to make the f of s function increase most rapidly. Following which direction you can make the function just decrease most rapidly and even zero change. Okay, so let's just call it a day here.